Thank you so much for coming to my talk. This is going to be an introduction to Scikit-learn. And it's also going to be a word of warning, because Scikit-learn is awesome, and it's so awesome that it makes it really easy to make models. And when it's that easy, it's really easy to make silly mistakes as well, because you have to think a lot about when you're making models. So we're going to talk a bit today about why Scikit-learn is awesome, and some of the things that you have to keep in mind when you're using that amount of power. So who am I? My name is Anders Bogsnes, as was so lovely pronounced. I'm from Norway, but I live in Denmark, and I'm a senior analyst at this company called Alm Brand. It's a Danish insurance, banking, and pension company that you've never heard about, but we do a lot of customer modeling across referrals between our different branches, that sort of thing. So we have a lot of data, and we're basically building a lot of models to use all that data. And we use Scikit-learn. And why do we do that? Because, in my opinion, this is the gold standard. If you talk to anyone in the machine learning universe that works in Python, they will always say Scikit-learn as number one. It's been one of the cool things about working in Python is that you have like one standard you can go to that everyone else has based it on. I don't know how many of you worked in R, but there is a more diffuse environment. So this is like a one-stop shop that you can get everything you need out of. And it scales really well. You can play with your toy data, your iris data sets, but we use it in full production with millions and millions of rows. Like, it is no problem at all. And how many people actually got this joke? I want to see how old I am compared to this room. Okay, I feel old now. The implementation is really, really rock solid. They don't take anything in that has not been very well tested. It takes a long time to put a new algorithm into Scikit-learn because they really want it to be well done. Some of the new stuff that's coming out now has been 4 years in the making, just added one new feature. And the API is great. Like this is definitely one of the most important things about Scikit-learn. They realized a long time ago that the API makes the library. So for any model, this is basically the pattern. You import your model, you instantiate it, you fit, and you score. 3 lines of code, you are now a data scientist, you have trained your first machine learning model. That's it. And it's the same API for everything. So if I want to train all the models, all I have to do is just instantiate a bunch of models, loop over them, and they have the exact same interface. So that's why it's really easy to just substitute different models and try out lots of different things very rapidly. You get that rapid iteration, which is so key when you're working with data. And everything is included. It really is like the Python philosophy of batteries included. You get your pipelines, you got parallelization built in, it's got pre-processing tools, and it's got lots of other nifty things that we're going to talk about today. And the documentation is really great. If you haven't had a chance, you might have seen this one wandering around somewhere on the internet. This is like how to pick your model based on your data. But they also have a user guide which goes into detail on each and every single model. It references the papers that they use to implement it. It gives you a high-level understanding of the math that goes into it. And they have lots and lots of use cases and examples. So the documentation is really great. But you're now data scientist. You just fitted a model. You saw how easy it was. So your boss comes and says, hey, I hear you, data science. So he gives you some data that he found lying in his desk. You know, they all have CSVs lying around, right? Can everyone see this in the back? Can I get a show of hands in the back over there? No? More? Better? All right. Sorry? Oh, it'll scroll. Don't worry. So I'm going to run through some live coding now, which is the best thing to do in a talk. We all know that. So I am going to, actually, can I get rid of some of this stuff up here? I might have to zoom. Yeah, that'll be okay. So we have our standard imports. We use pandas, numpy, matplotlib, just to get some, and we put some settings. And then we have this here data set. Now this is not a Alm Brand data set. This is something I found on Kaggle. It's a great resource for looking up random data sets to try out different things if you want to show non-proprietary stuff. And it looks kind of like this. So this is a travel agency in Singapore, and they have given us some data about some travel insurance that they've sold, and whether or not those people made a claim or not. So we know a bit about the agency, what type it is, was it sold online, the product name, the most important one, did they claim or not? How long was their trip, destination, yeah, and a bit of other things. And that's a bit stuck. We have about 63,000 rows. Not big data by any means, but like it's some data. So first things first, machine learning models do not like strings. They're maths like numbers. So I'm just going to do some very light pre-processing. I'm not going to talk too much about it, but I just want to show you the results. So all the numbers are the same, but for example, the agency is now what we call one-hot encoded. So if I want to say that an agency is ADM, or in this case C2B, it gets a 1, and all the other columns get a 0. It's a very common method of encoding these strings, so that we can get information about what they're called. Yeah, the different categories into our model as well. I also put an unknown gender for the places where we don't know. Yeah, it's very light pre-processing. I would like to point out we're not going to end up making a good model. We're going to end up making a model, and we're going to see all the problems that we're going to have on the way. So that's why I'm not doing a lot of pre-processing. And now, just as promised, from Scikit-learn and linear model, we import our logistic regression. We make our classifier. We fit to our data, and we score it. And voila, we have just made a model that 98% of the time predicts whether or not there is a claim. We're done, right? That's awesome. We can go to our boss, put it in production, and we make millions. I've just committed lots of cardinal sins right now. But I've seen people do this. I actually know big companies that have done exactly this. So my first cardinal sin is I am cheating at the exam. I have given my model all the answers, and then I ask it to predict the same answers I just gave it. Like, that's obviously not a good idea. So of course, Scikit-learn to the rescue. We have train test split. It's just a utility function that takes your data and just splits it into 2 parts, so that we can use one set for training on, and then we can validate it against a holdout set that the model has not seen before. So there is some random states. Just make sure that the random numbers are the same every time I run it, so that we can reproduce our results. And then the stratify. I won't talk about that too much, but it's quite important, which we'll get back to later. So now I'll do the same thing again. I have my train and my training data and my test data. So now I'm no longer cheating. I still get an accuracy of 98.5. Like, awesome. I've now, absolved myself of my cardinal sin, and I still get a really, really high accuracy. We're done, right? Into production. Not quite. Anybody want to guess what's going on here? Very good. What's the model actually doing? So if we make a little prediction here, and then we sum up all predictions and compare to how many were actually claims, our model predicts that there is 1 claim out of 63,000, well, not quite 63,000 because it's the training data, but there were actually 232. So my model just said that there will never ever be any claims made, which, as an insurance person, I can tell you is a really bad business decision. And our problem is right there. Most people do not have any claims. Luckily for us, or else we wouldn't make any money. But our model takes the path of least resistance. It's not, as a computer, it's not intelligence. If the path of least resistance to get the highest score is just to guess that it'll never happen, it'll just do that. So that was the two first cardinal sins, and I've seen this so many times. Some person who knows Python very well imports their logistic regression, fits it, and hey, 98% accuracy into production. So what can we do? Well, first of all, our problem is that we're using the wrong metric. We are using a hammer where we need to use a screwdriver. Because accuracy is correct. Like, this is exactly what the model is doing. But we need to balance this trade-off between trying to get all the positives and not getting any of those negatives. So we want to capture all these 232, but we also don't want to just guess that everything is a claim. So we have this concept of the ROC curve. This is a lot of code, but basically all it does, it uses, again, Scikit-learn's built-in utilities to give me a ROC curve and a ROC score. That got a bit loud all of a sudden. Oh. I think it's... Is that better? All right. So all this is just some plotting code, but the meat of it is you make your prediction with a probability, and that's one of the cool things about when you're doing these. It's not a 1-0, it's actually giving you a probability of something happening, and then you just translate and says, oh, it's over 50%, then it's a 1, or else it's a 0. So you can get those raw probabilities out, and then we can use this utility function to get our ROC score. It also has a utility function for making this ROC curve. And what is this, you might ask? So the idea here is that because we're getting these probabilities, who says that 0.5 is the correct threshold for cutting off? We just saw that our baseline is 1.46. So having a threshold of 0.5 is probably a bit much. It's a bit of a stretch to reach that. So what the ROC curve does is that for each threshold that is possible, it tells you how many of the true positives did it get, like how many of the claims did it actually pick up, compared to the false positive rates. Out of all the ones it guessed to be claims, which ones were false? So this gives you a much better view of what's actually going on in our model, because it's not as simple as 0.5 good, under 0.5 bad. And the ROC score up here that you see, that's basically just the area under that curve, and that the line in the middle, that's just random guessing. So we want to get our curve as much as possible up into the upper right corner for me, left for you. That would be the ideal model. So a ROC curve of 0.04 is actually not that bad. It shows us that we're using the wrong threshold, and that's something that we can play with. And that's, again, a business decision. How many false positives are we willing to accept in order to get some true positives? There are other metrics as well, and of course Scikit-learn implements a bunch of different metrics. Again, the user guide is a really good introduction to this. We have the F1 score, precision score, and recall here. So the precision score is a number that gives you basically the one of the axes. Every time I predicted something was positive, was it actually positive? So how confident am I that when my model says that you are going to make a claim, that it's actually going to be a claim? On the other hand, the recall says, out of all the claims that there were, how many of those did we actually pick up? Like, is it very important that I get all the claims, but I'm maybe willing to sacrifice some false positives? Or do I want to be really, really sure, because maybe I'm going to contact you and do some action towards the customer, so I have to be really sure that you're going to have a claim before I do something. So these are like the trade-offs that you always have. And the F1 score is trying to balance these two things. It takes the harmonic mean of those two numbers, and it's also something that you can use to tune your models. But again, you always have to think about, what is it I'm trying to achieve? What is the goal of my model? Am I just sending an email to someone to help them out? Maybe then I want to favor just getting everyone. Or am I going to cancel your contract because I think that you're going to have lots of claims? I better be really sure about that. But it's okay if I don't catch them all. So on this model, because we haven't set a good threshold, we are getting zeros all over. So before, we tried a logistic regression, but Scikit-learn implements so many other models. So often what I like to do is just use this fact that the API is exactly the same. Just import a bunch of different models that kind of cover different ways of looking at the data. So here we have a logistic regression, gradient boosting classifier, naive Bayes, random forest, k-neighbors, and this one right here, my favorite, the dummy classifier. So the dummy classifier is a way of saying this is the most naive model you can possibly come up with. It's basically a random guess. If your model cannot beat the dummy classifier, you are doing something wrong in your data. So always include the dummy classifier, because you are going to make some mistake in your code somewhere, and you're not going to catch it unless you have benchmarked your model against the most naive model possible, like just guessing that no one ever makes a claim. So we just loop over all these models, and then we get the ROC score, and we can see that the gradient boosting classifier narrowly edges out these other ones. But logistic regression is really good. And that's another thing I want to point out. Like, neural networks are really hot, and everyone wants to use gradient boosting, XGBoost. Regressions are not that bad, and they have a lot of other cool properties. So don't get too sucked into the hype. So another thing, all these models have all these different hyperparameters. So this is the gradient boosting classifier. These are all the different knobs that I can tune on my model to try to get a better model out of it. And I can change one of these from let's say I want max depth of 1, and then I'll fit and score my model, and it's 8.37. Okay, that was slightly worse. And I can change that to 5, and I can load check again. But we're computer scientists here. We have a computer. I'm not going to go and do this by hand. So of course, Scikit-learn gives you a nice little handy wrapper called grid search. So grid search works by you specify which parameters you want to tune. So in this case, I just want to check out some different learning rates and some different max depth. And then I just make some lists of all the different parameters I want to try out. So what the grid search will do is that it'll go through each combination of those parameters. So in this case, I'm doing 3 by 3, so I'm going to do 9 different models. That's also something to keep in mind. If you have a big data set, and you're going to be training hundreds of models if you're trying to find the right parameters. But the really cool thing here is that, again, Scikit-learn to the rescue. This little nJobs parameter. If I look at my HTOP now, it's using all 4 of my cores. Now finished, so I wasn't quite fast enough. We'll do it again. But it automatically multiprocesses your models. So if you have 100 cores, you can just type 100 here, or -1 to just say use everything. And Scikit-learn takes care of the parallelization for you. So you don't have to write all that code. And it gives me the best score, the best parameters, and it gives me this nice little dictionary, which I turned into data frame, of all the different parameters that it found on the model. Oh, if I can scroll. So now I can actually really go in and start digging into, okay, what actually worked, what seems to be, decent numbers. I can go back to my grid search. I can start maybe expanding, shifting my parameters. So I can start, tuning my model a bit. So if you might have noticed that I said we were going to use 9 models, but up here, we're actually doing 27 models. So, and this is what we call cross-validation. Because I'm almost committing the same sin I did before. I might not be using my validation data to train my model, but I'm constantly comparing. Like if I was to do this for real, I'd probably be doing hundreds and hundreds of comparisons to my test data. So I'm tuning my model to more accurately predict better on my test data. So that's almost the same as if I just gave it my test data and say, hey, try to predict this. So in order to solve that, we have come up with something called a cross-validation. And I want to give you an example of what that is right here. Scikit-learn, of course, implements many different varieties of cross-validation. This is the most simple, called k-fold. So I just take the first 21 rows of our data, and then I do our first splits. I ask for 3 splits in this. So in my training data, out of those 21, 14 are now in my training data. And here it gives me the indexes. So 7 through 20 are now my training data. And 0 through 6 is now my test data. So I'll train my model on this new training data and try to predict on this test data. We run the next split. And now you can see we again have 14 rows, but now we're doing 0 to 6 plus 14 to 20 is our training data. So we divided our data into 3 sets, and we're taking 2 to train on and predicting on the last one. So this is a way of kind of artificially generating more training data so that we don't tune our model too much to this holdout data we created in the beginning and commit another cardinal sin. Ooh, did I do it again? There we go. So as I said, there's a lot of different k-fold varieties. To use your own, you basically just create a k-fold instance. You get your model ready. Then you get your accumulator ready. And then you just do cv.split on your data. And this will give you the indexes of the data that you need to index into for each split, so that it doesn't actually pass you the entire data every time. So you just index into your training data through every time, fit your model, create your prediction, get your score, print it out, and append it. So if I run that, I start getting this for each fold. It'll start giving me some scores. So this is kind of nice because I'm getting fairly consistent scores. So that's what we're also getting this mean and the standard deviation in the end, because it's good to have an idea of like how wide of a range do I actually have on this accuracy. See, now we're getting like down to 77, from 86 to 79. So I'm kind of getting like kind of all over the map. So that says something about that maybe I need to work a bit on my parameters. Maybe this model is not the best. But it is fairly consistent. It's not a huge range, but I would be a bit worried about this, this diversion. But of course, this is Scikit-learn, so there's a hard way and there's an easy way for everything. So you can just use this crossval score function, which does exactly the same thing I just did before. And on top of that, it gives you that free parallelization that we saw before. So if you're into doing this, and you don't need to do anything custom, Scikit-learn always lets you do custom stuff. But there's always these helper functions that have these nice little extra features. So now we can run that, and if I'm fast, now you can see it's a bit dark, I know, but all my 4 cores are at 100%. I'm using the full power of my laptop instead of just using a single core. So that took 11 seconds, and I get kind of the same score, which is what we would expect. So to round out, you also need to understand what your model is actually doing with your data. And Scikit-learn implements feature importance on tree-based models, but also gives the coefficients on the regressions. And this is something that you have to do an active decision. Not all models will give you a feature importance or a coefficient to see what data is actually using. So from our grid, it actually acts as if it's the model. I can call it best estimator, so I get the best model from my grid search before. And I want to see the feature importances. So that's a kind of arbitrary number that ranks each feature, how important it was to the model to give a prediction. So if we look here, we can see, okay, this agency, there's definitely something going on here. So at this point, I would go back over to the business side, and I talk to the guys back home and say, hey, what's up with this agency? Is it that we're selling a lot to them? Are they just really bad? Are they in a bad neighborhood? That sort of thing. Oh, don't make any conclusions on it yet, because there might be a really good reason for it. It also doesn't give you whether it's a good thing or a bad thing. It just says this is important. So it's not telling me that policies sold by C2B have a lot of claims. It's just telling me that to make a prediction, this feature is very important. It also tells me that all these other things are actually not very important, which is also a really, really nice thing to know, because it allows you to throw away a lot of data that you don't actually need and keep the same performance. So if you have 1 million rows and maybe you have 200 features, not uncommon, that's a lot of crunching. So if you can eliminate some features up front, that is going to save you a lot of time, and also prevents spurious correlations that you might not have noticed when you're working with your data. So we also have linear regressions. And using these coefficients, we now get a direction. So this is one of the reasons why it's really cool to start with regressions, or logistic or linear, because it gives you a much better idea of what's actually going in your model. It gives you a concrete number that is multiplying that feature by in order to get the prediction. So now I'm getting some different results. I'm actually seeing that C2B, that's a really good thing. Well, actually, really bad thing in this case, because they're making claims. So the C2B, it would be multiplied by 1.5, which is quite big compared to these other ones. I also see that online, all of a sudden, it is actually a really good predictor for them not having claims. So for some reason, it looks like online is a really great way to distribute insurance. We also get this other agency, a TST, which apparently is also really good. But notice I'm getting different results from my gradient boosted classifier and from my logistic regression. There was a really great talk yesterday in this room actually about someone who was ensembling models. So basically they were taking lots of different types of models, getting the feature importance, and then getting them to vote on what was the most important feature for that model. And the idea there is that all these different models are looking at your data in different ways. In the same way that in the beginning, I tried out lots of different models to see which model worked best on this particular data. It's the same thing with these feature importances. Because they examine the data in different ways, they will find different things in your data. So trying out different models and looking at what each of them think is important and trying to see like where do they agree and where do they not agree, that can be a really important step in trying to figure out what is actually happening in your data. Because sometimes you do have random coincidence. Sales of ice cream goes up when people get murdered in Chicago, sort of thing. Normally, I would also do, because it's a logistic regression, it gives us values for pretty much all of them. So you can see that none of them are actually unimportant. They're just a small weight. And that can be a bad thing or a good thing depending on your point of view. If you're trying to approach this from, I'm trying to get rid of a bunch of features, then this is not that helpful. It's like you can probably put some sort of cutoff and say, I don't want anything less than 0.5. You could also go and say, I want to use a model that actually penalizes features that don't seem to be doing much. And there we have ridge regressions, elastic nets, and lasso. So they're all very good for, they give you an extra penalty if you're just like hanging around for the ride. So they'll be more towards 0 if they're not important. So those are also some excellent ones to check out if you're just trying to use this to get rid of some features. So in conclusion, we have talked today about the importance of doing train tests. Don't let your model cheat at the exam. We have talked about choosing the right metric for the job. The default one, .score, is not always necessarily the right one. Scikit-learn does have really, really good defaults, but you always have to think about what is my problem, what is the product that I am building, what is going to be the end use of my model. 98.5% accuracy sounds really good, but if I'm actually trying to predict who has claims in order to do something, it's not very useful. We talked a bit about hyperparameters, that they have all these different knobs that you can turn in the models, and how we can use grid searching to try to find some of these really good knobs. We talked about cross-validation to try to avoid the sin of tuning our model to try to predict our training data, our test data, sorry, over and over again, so that by proxy you're actually just giving it your test data. And we talked a bit about feature importance. So those are a few things about Scikit-learn. It's a vast library, and it has lots of other different cool things that I have not had time to go into today. There are many talks I've given on Scikit-learn and all it can do. But if you're interested in that, just come up to me and have a chat. I'll be happy to answer any questions you might have on that. And I just want to leave you with the same thing I said when I started. It has never, ever been easier to train models than it is today. That's also deep learning with PyTorch and Keras, and it's also all these different models that Scikit-learn implements. That just puts a bigger burden on you as the developer / data scientist / analyst to think about exactly what it is you're trying to do, because you have this abstraction layer that's doing so much magic for you that you really have to take the time and think about what is it I'm trying to achieve and what product am I trying to build. And with that, I'll say thank you very much, and thank you for your time.
Have you got perfect? Can you please raise your hand? Just you? Okay, perfect. I see 2 hands.
Great presentation, actually.
Thank you.
You mentioned that you shouldn't get caught into the hype about CatBoost and XGBoost. I did get caught into it. I was wondering if you could elaborate a little bit on what's better in Scikit-learn than, say, just using CatBoost, for example. especially with categoricals, the feature importance, the fact that it's one-hot encoded, it seems like it makes it not as easy, like to understand how big a deal is which agency is selling the insurance product, especially if you have a lot of them.
So, I mean, Cat Boost is a really great library. It's very new, so that's one thing. Scikit-learn is battle tested, and it's been, tried for 20 years plus, almost, yeah. But the most important thing I would want to say is that always, always, always start simple, and then work your way up. Like I've worked with Cat Boost, it can be sometimes a bit tricky to get going and get your data to fit it. And if it's not giving me a significant advantage over linear regression or logistic regression, then keep the logistic regression, which is something that is known, something that is easy to implement. I can give it to my production guys, and they can write it in SQL. And then I can work on getting the advanced model because every day my model is in production, we're getting some value. If I'm getting 5% value every day while I'm working on the advanced model, it's like, that's awesome. And then I can add, another 5% when I get the more advanced stuff going. And that also goes for your deep learning and your neural networks and that sort of thing.
Other questions? We have some minutes left. Okay. So I think that we can just thank you and have a nice day.
Thank you very much.